Hello, everyone. My name is Adam Meyers, and I'm with the Department of Industrial Engineering at Penn State. This is joint work with my colleague Mohammed Buqammaz and my advisor Hui Yang. And I'm going to be talking about cross-recurrence analysis for pattern matching of multidimensional physiological signals. Here's a brief outline. I'm going to talk about physiological signals and how cross-recurrence plots relate to them. I'm going to give you my methodology, which involves cross-recurrence analysis, self-organizing network, and clustering in its evaluation. And I'll give you a VCG data set case study, and I'll give some concluding remarks. This is just a brief overview of the cardiac electrical activity of the heart. And so the heart undergoes electrical conduction, which causes the heart muscles to contract, and it leads to a heartbeat. And we can measure this electrical activity by placing electrodes on the body, as you can see in the middle picture. And we place, the most common is 12-lead ECG. So the 12-lead ECG places, the standard is to place 10 electrodes on the body, and it measures the electrical activity of the heart from 12 different angles, right? So the leads are like angles. And on the right-hand side, you see the examples of ECG signals. So each one of these waves represents a heartbeat. And from this information, we can determine if the heart's functioning normally, and we can also, cardiologists can diagnose patients to see if anything is wrong. And so that's the standard is 12-lead ECG. I'm going to be looking at vector cardiograms. So vector cardiograms can be assembled from 12-lead ECGs, and it combines that information from the 12-lead ECG into 3 leads. So instead of 12 angles, you now have 3 angles, and these represent the X, Y, and Z axes. So the VCG gives you both spatial and temporal information about the electrical activity. It gives you both magnitude and direction of the electrical forces. Here are some examples of, there's 12 examples here actually of 3-lead VCG. On the top row, my data consists of 93 patients comprised of 3 groups, and with 31 patients each. And the 3 groups are healthy control, represented by HC, left bundle branch block, LBBB, and my own myocardial infarction, represented by MI. So this top row shows the intragroup comparisons, comparing VCG signals between 2 patients within the same group. And the bottom row, the intergroup comparisons, shows compares 2 VCG signals from different groups. And you can already see similarities and differences, right? The top row has more similar patterning, amplitude, etc. And the bottom rows, signals are very different from each other. So what I want to do, and what I'm going to propose in this study, is to leverage the cross-recurrence plot to try to capture the similarity and dissimilarities between signals, and see if it can accurately distinguish between patient groups. And so on the right-hand side, these are the cross-recurrence plots of the same signals shown on the left-hand side. And what I'll point out, I'll go over the cross-recurrence plot in a little bit more detail later, but what this shows, this essentially is just a Keller map, a heat map of spatial distances between the points in the VCG signals, Euclidean distance. And so blue means that the points are close in distance, and red means that they're very far away in comparison. And so what you notice in the top row is that there's the prevalence of these main diagonals, right? So main diagonal is clearly here. There's a rough main diagonal here and a distorted main diagonal here, but it's still occurring, right? You have mostly blue here. It's not really interrupted. But here they're interrupted by a dark horizontal band, right? So you don't really have, in each of these, you don't really have the main diagonal that you see in the top group. So that leads us to the hypothesis that the diagonal line measures, the CRP, you can get diagonal, vertical, horizontal line structures from the CRP. And we'll conjecture that the diagonal line measures are particularly important, just based solely off of this observation. So here's the overall methodology for pattern matching of physiological signals. And so we take compare two VCG signals from two patients, and we compute the cross-recurrence plot. And from the cross-recurrence plot, we can get certain quantitative measures, again, based off of these diagonal, vertical, and horizontal line structures. And take one of those diagonal CRQA quantitative measures, take one of them, and we can use that as a basis for a dissimilarity matrix. So between patient I and patient J, for example, we can compute their cross-recurrence plot, compute one of the cross-recurrence quantification measures, and that can be used as a dissimilarity measure between the ith and jth patient. So that's what this matrix is showing. This is for a single CRQA measure, and it compares all patients, all pairwise comparisons. Once we have this dissimilarity matrix, we can then extract a self-organizing network from it that shows 3D locations of nodes, of patients. And this also serves, this self-organization network also serves as dimensionality reduction, where we can reduce this n by n dissimilarity matrix into essentially an n by 3 matrix, where the 3 columns represent the x, y, and z components of the spatial locations of the nodes. With the node locations known, we can then perform clustering and then compare the clustering output with, since we have the known diagnoses of the patients, we know if they're healthy control, myocardial infarction, or left bundle branch block, so we can compare to the known diagnoses. So I'm going to talk about each one of these in turn. The cross-recurrence plot is computed based off of this equation. It's a simple equation that if signal I and signal J this is looking at each component of signal I and signal J, so you compare all components, all pairwise components. And if those components are close enough to each other, then if they're within an epsilon distance of each other, then you put a black dot on the cross-recurrence plot. If they're not, if they're above the epsilon threshold, then you don't put anything. It's just a white dot. You can think of it as. And so with the black dot, so notice that this is now black and white. Before I showed you this is color-coded, right, which is a heat map. So essentially that color-coded plots we're showing you without the epsilon. Now once we threshold, then we create black and white plots. And these black and white plots will show you more clearly what I was talking about before with, you see the presence of this main diagonal here, right, in all of the top row, the comparisons within groups. That doesn't exist when you compare across groups, right? So again, conjecture that these diagonal line measures are particularly important. You also see, you have these rectangles here. That's showing horizontal, vertical, and diagonal line structures. So those seem to be pretty common. It seems to be more the main diagonal and the diagonal line measures seem to be more important for distinguishing. And so why are we using cross-recurrence plots? There are other measures, other methods for similarity assessment between time series signals. So one of the most popular being, one of the most successful being dynamic time warping. So that's shown on the right-hand side here, B, where you just take a signal and you try to align it with another signal by stretching and shrinking it. And this has some disadvantages where you have to align all components of one signal with all components of another signal. And you have to match up the endpoints as well. So you can end up matching up points that shouldn't really be matched up. And what the cross-recurrence plot does instead, it has several advantages. One advantage is, I don't want to talk too much about this, but one advantage is phase space reconstruction, where you can think of a 1D time series and you can reconstruct it in a time-delayed phase space into, say, 3 dimensions. And so from a 1-dimensional signal, you get a 3-dimensional signal. And then you can perform comparisons on that 3D signal on the trajectory of that 3D signal in phase space. And so one of the main advantages of doing this is that it reduces the effective noise. CRPs and recurrence plots in general are also very useful for highly nonlinear, non-stationary signals, and I already mentioned the noisy signals taken care of by phase space reconstruction. And the third one, the most important one for our purposes, is that the cross-recurrence plot can identify common patterns at arbitrary positions. So you're not just taking two signals and you're trying to align them like in dynamic time warping. You're looking at all the common patterns at arbitrary locations between the two signals. So once we have the cross-recurrence plot, we can extract quantitative measures from them. These are the already established ones in the literature. So you have the overall measures such as recurrence rate. Recurrence rate is simple. It's just the percentage of recurrence points occurring in the recurrence plot. And you also have diagonal line measures and vertical horizontal line measures, like I mentioned in the first few slides. we're going to propose a measure, another cross-recurrence quantification measure for this paper. It's called R-tau max. And essentially what it does, so this is just a quick example to show you what it does. And this is a 5 by 5 cross-recurrence plot. Very simple. Usually they're much larger than this. But this is just an illustrative example. And again, the black dots represent that a cross-recurrence point has occurred, and white dots means they don't satisfy that epsilon threshold. And what this measure does is it looks at, so the main diagonal is you're just comparing each signal, both signals to each other along the, according to their normal time arrangements. If you go above the main diagonal or below it, then you shift one signal relative to the other. So you start considering time delays. And so with this diagonal above the main diagonal, this could be shifting one of the signals up one time unit and comparing it then to the other signal. And so what my measure does is it looks for the maximum number of recurrence points that occur along one of these diagonals. So in this example, it occurs right here with 3, right? So along this diagonal, 3 recurrence points occur. Whereas in the other ones, the next closest is 2 recurrence points here and 2 recurrence points along this diagonal. So our tau max in this case would be 3. And so what this does is it helps us to characterize the maximum similarity between signals, overall pairwise time delayed alignments. And this is in contrast to, say, L max, which is a previous one, this one, L max. This is the length of the longest diagonal line in the cross-recurrence plot. So the length of the longest diagonal line is actually 2 in this case. It occurs here, and it also occurs here. But in our case, we don't have to have them consecutive, right? So they don't have to be subsequently occurring recurrence points. As long as they're belonging to the same diagonal, then we count them. So again, this characterizes maximum similarity between signals. Once we have the cross-recurrence quantification, we've performed that, we've come up with a dissimilarity matrix based off of that, then we can perform self-organizing network. In this network, the nodes represent signals and patients, signals or patients. And what this self-organizing network does is it looks at all pairs of nodes, and between each pairs of nodes, there's an attractive and a repulsive force. And so those two nodes attract and repel each other. And this is happening for all pairs of nodes. So you have a network that's contracting and expanding until it eventually settles on some kind of stable layout. And that stable layout is a layout of minimum total energy, or minimum total force. The force on node I is represented by this equation, where the top term is the repulsive force and the bottom one is the attractive force. And you have tuning parameters, which I don't really want to talk about. Y is just the current spatial locations of the nodes. The most important thing, the thing that really drives the organizing network is the dissimilarity, right? So if two nodes are highly dissimilar to each other, then they're going to tend to repel each other. Whereas if they're not dissimilar or they're highly similar to each other, they're going to tend to attract each other. So based off of the dissimilarity matrix that we obtained from cross-recurrence quantification analysis, we can obtain a network via this algorithm. And I'll show you a video of that later, of how that looks. The other two steps in this is clustering and evaluation. I don't want to talk too much about this because it's not the focus of this paper, but we just use a regularized k-means for clustering. For evaluation, we do both internal and external evaluation. The internal evaluation measures the silhouette statistic. Internal evaluation just measures how compact, how densely clustered the nodes are. So if you have, if your nodes within the same cluster are densely packed and nodes from different clusters are highly separated, then that would result in a high silhouette statistic. The external measure is normalized mutual information. So what this does is it allows us to compare the clustering output from our methodology to the ground truth with the healthy control, myocardial infarction, etc. And so the normalized mutual information is scores between 0 and 1, with 1 being perfectly matched clusters. I've already described the data set, so I just want to point out that this data set is from the James A. Halley Veteran VA Hospital in Tampa Bay, Florida. And this is from my advisor's paper. He used to work at University of South Florida, which is located in Tampa Bay. This is the experimental design for our experiments on the VCG case study. The only thing I'm going to point out here is that we did both, we did two types of VCG signals. We did the VCG signals under their normal scale, and we also rescaled them. So the rescaling the VCGs was to reduce the effects of amplitude. The cross-recurrence plot is highly distance-based. And so we didn't want two signals that may differ a lot in amplitude, but otherwise are very similar. Maybe they're similar in their global shape, their spatial orientation. We want those two to match up. And so what I did is to try to achieve better results is I rescaled the VCGs so that their amplitudes of all the VCG signals are 1. And that places more emphasis on the shape of the trajectories of the VCG signals. Okay, here are some results. This is the CRQA-based dissimilarity matrix. This is for the unscaled VCGs and rescaled VCGs. For the unscaled VCGs, this is showing Lmax, again, the length of the longest diagonal line in the CRP. This one performed the best, so that's why I'm showing it. To read this, you can look at this block diagram. So the main diagonal shows intra-group comparisons, so comparing patients within the same group. The off-diagonal shows comparisons between patients from different groups. And this is symmetric, so you don't need to look at all of it, just one of the off-diagonal upper or lower triangles. What you notice in the main diagonal, so the comparisons of patients within the same group, is you notice a lot more blue, right? And so blue represents low dissimilarity or high similarity, right? So this is what we want. We want a lot of blue along the main diagonal, and we want a lot of red, orange, and yellow, like we see on the off diagonal. So that's showing that Lmax is able to distinguish correctly between the three groups. And we see something similar for Rmax tau, which is the proposed measure, which happened to perform the best for rescaled VCGs. So I want to show you a video of the self-organizing network. This is the best clustering that we got. This is from Lmax. And what you do is you start off with a random network layout. And then the forces act on each other. The nodes attract and repel each other until they reach a stable layout. So they started off very uniformly distributed, again, they're random. And now they're pulling. The attractive forces are overwhelming, so they're pulling themselves towards each other, and then they start to repel, and they start to settle into the accurate patient groups, right? So you can see the blue, red, and green are all clustered with each other. Here's a table of the results. I just want to point out that, again, LMAX did the best. It had an 88% or 0.88 NMI score. So that's the external evaluation measure. So that means that LMAX produced a clustering that was very close to the ground truth. Here is a picture of that clustering. So you see the true diagnoses are labeled. They're color-coded in the different shapes. And the circles in the represent the clusters that were output by our methodology. And so they actually almost perfectly match the ground truth, but what you notice over here is that there are 4 LBBB patients that ended up being grouped with being clustered with the myocardial infarction group. So it did incorrectly cluster 4 patients. Under the rescaled VCGs, again, the proposed measure performed the best with an NMI score of 0.82, and it performed significantly better than the other NMI in the other CRQA measures. Okay, so just to conclude, I presented my methodology for pattern matching of multidimensional physiological signals. These signals are highly nonlinear, non-stationary. In our case, they're also spatiotemporal because we're using VCG signals. And it showed that our methodology performed pretty well, with, again, LMAX performing, the diagonal line measures performing particularly well, with LMAX performing the best. And whenever the VCG signals are rescaled to reduce the effects of amplitude, our proposed measure, Rmax tau, performed the best. And so this shows that CRQA does have the potential to accurately distinguish between patient groups. Okay, here's the contact information. Feel free to contact any of us. And thank you very much for your time.